Welcome back. We are looking at LU factorization, which is just like how factorization works with if you're looking at, wow, it's a really big pen. If you're looking at say 6, that's 2 times 3, but it's not unique, right? We can also factor 6 as 3 times 2 and 1 times 6 and so on. So LU factorization is a way that we can break up a matrix A, and if we break up that matrix into a invertible lower matrix, invertible matrix that has some zeros, and then a unit lower triangular matrix that also has some zeros, then it actually makes our computations a little bit faster, which is kind of nice. This is a pretty cool diagram, I think. So we have multiplication, where if we're looking at ax equals b, right? We could just multiply by a, or we could take this x and multiply by u, because let's say that a equals L times u, and that's not a dot product. That's just a regular multiplication. So in order to get our answer b with our L and our u, we're going to have x times u, and that's going to get multiplied by L afterwards to end up with our b, as opposed to just multiplying a times x to get b. So let's look at how to deal with that with the speed of how these two computations run, just to be a little bit more motivated for how why we would want to do this. So here we have some MATLAB stuff. So and I also included the text of what this is over here on the left, but I'll link this as well. So we have a matrix A. And so let's just, so this matrix A that's being suppressed, but we also have B, and then we're augmenting a matrix to have A and B together. And then we're going to time with tick and then talk how long it takes to find the row reduced echelon form to RF this augmented matrix, so we get a solution. And then we're also going to declare L and U, which are the LU decomposition of the LU factorization of A, and then do the intermediate step of having an augmented matrix with our B, with our L, the lower the invertible matrix that we had from before, and then have that RF to take that last column and then augment it with our unit triangular matrix, and then RF that and time how long that takes. So it would be so the timing that we're looking for is for this to take longer than this. So let's see if it works. So the elapsed time for the LU factorization was 0.00715 seconds, whereas the time it took for the row reduced echelon form just on our augmented matrix was 0.0144. So it's about twice as long, which is that's pretty cool. That it and this is only working with like a 4x4 matrix. So imagine if we have bigger matrices, how much faster it will be. So how do you perform LU decomposition or factorization? Well, you reduce A into echelon form, so you do your row operations on that, but you also keep track of the row operations that you were doing, and you kind of hold them in L because they're elementary row operations. So those are all operations that you can represent through matrix multiplication, right? And so we have our kind of like record keeping happening for L, and then and U is being row reduced. So try that out. Pause the video and try that on this problem, and then we'll see how we do. Pause the video. So in general, we know that A has got to be L times U, And how do we get this? Well, this L is going to be the inverse of all of our elementary row operations that are happening, however many we need, times L, times our U in order to get back our A. So we can think through, well, L needs to be so this is going to be inverses of elementary operations, and then also this this needs to be able to multiply our like elementary operations, the product of those, however many we need, multiplied by our L, has to give us our identity matrix. And so since we are assuming that L is invertible, so L's got to be invertible, so that means it needs to be square, and it needs to be 4 by 4 because we have 4 rows. And how are we going to use elementary row ops for getting echelon form on this? Well, we need, well, all of these, they seem to be, we can handle these because they're all multiples of each other, right? So we have one of those, and then we have like -2 of those, and one of those, and -3 of those in order to get out our zeros, all down here, all over here. And then what else is happening? Well, let's parse through this with a little bit methodically. So we end up with, oh, that's a bad 0. So we get zeros there. And then what's going to go in these gaps? Well, what do we need to do? Well, in order to keep track of everything that needs to happen, we're also gonna keep track of the zeros that we have. So we've gotten 2, 4, -1, 5, and -2, but we zeroed out everything down here, and we haven't changed 4, -2, so that's going to be with 3, 1, 2, and -3, and then here is going to be what, 4, 2, so -9, 2 is 1, -3, -4, 10, and then we need 4, 2 is 12, 4, 12, and -5. And so we've kept track of the elementary row ups that we're using here, and how we've reduced. And then in order to zero out what we have over here, with these, we'll need to multiply by what, 3, -4 in order to zero those out. And then, so that means that here we have 2, 4, -1, 5, -2, 0, 3, 1, 2, -3, 0, and then 0. Oh, that's 0. This will give us 2 and 1, and then 0, 0, 0, and then 4 and 7. So we have another set of like row operations that we're doing. We have zeros here, so I guess that's nice. And then we just got to deal with a little bit more. So this 2 and this 4. So to deal with this 2 and this 4, we need a 2 here, which means that when we're doing our row ops, our top rows stay the same, 2, 4, -1. Zero, 2, and 1, 0, 0, 0, 0, -2, So that's 5. And so here, what we needed was that 2. And then we have a full L that we can multiply by this U, this is our resulting U. So L, U, multiplying L and U is going to give us A. So what we did was effectively keeping track of our row operations that we did with no swaps, and doing our row reduction so we get echelon form. We don't need reduced row echelon form, but we do need echelon form to get a U. This is not unique. However, this is following our straightforward algorithm of keeping track of our elementary row ops and then multiplying. And then finally, we got some numerical notes. So if we're working with like a pretty big matrix, like bigger than 30 by 30, because our examples were kind of small, they were like 4 by 4 and stuff. But if we were looking at a dense matrix, so it's non-zero mostly, as opposed to sparse, which is more zeros, then if you like thinking about how many operations we need, then doing LU factorization takes 2n cubed over 3 flops, which is about the same as doing row reduction. And that makes sense, right? That the things that we're doing are pretty much just like row operations. Whereas if we're finding a inverse, that takes about 2n cubed flops, so like 3 times as many flops. And solving our broken up system, where we're taking L first and then we're looking at U, that takes 2n squared flops, so less flops, right? And then multiplying by A inverse is also going to take the same number of flops, but it's not necessarily going to be accurate because we are going to have some rounding error due to A inverse and then doing more operations with A inverse. And if we have a sparse matrix A, then doing our LU factorization will give us L and U sparse as well. And sparseness is nice because then we have more zeros, but A inverse will probably be dense, and so it's definitely way better to use LU factorization for solving big systems. All right, I think that's it. What did we do? We found a LU factorization. We thought about our algorithm. We looked at an example, and there we go. All right, bye.